Welcome everybody, I'm glad to see you've returned. What we're going to do is start with a review of last week in the form of a 3-minute video. It was produced by, well, the video is 7 minutes long. We're going to show 3 minutes of it. It was produced by Scientific American a year ago, and it will be a good review of what we talked about last night. So let's do this.
This is the picture we've all been waiting for. The deepest image of the cosmos ever captured. Humanity has never seen so far back and so clearly into the depths of the universe's history. The multitudes of nameless galaxies you see here emitted their light more than 13 billion years ago, mere cosmic moments after the Big Bang. This one image, and the countless others to come, has been the result of more than 2 decades of focused efforts by some of the world's greatest scientists and engineers. From concept to construction and testing, from launch to deployment and commissioning in the frigid depths of space, from opening its new eyes in the cosmos to gathering and processing the data to ensure it sees more clearly than ever before.
30 years from now, when we look back at the most amazing science from Webb, half of it's going to be what we plan to do, but half of it's going to be some really fascinating science that we haven't even yet thought of.
Those are just the first images. Think about many years of images and other things we're going to learn with this telescope about potentially habitable planets. We're going to learn a lot of that over time, not just the first images. And I can't get my head around what it might be.
Our time machine is the James Webb Space Telescope, or JWST. A one-of-a-kind observatory built to unveil how the universe first began to shine, and much, much more.
The first year of Webb Science is going to be very exciting. The programs that we have been planning for 20 years, most of them will be executed during this first year to see the first light in the universe, the first galaxies that formed. We will probe the atmospheres of planets around other stars. We will get our first look at the surface chemistry of objects in our solar system that are just too faint for our current telescopes to see. The science is going to flow, and it will be amazing.
It's the largest, most ambitious space telescope ever made, and promises to produce some of the most incredible discoveries of our lifetime and beyond.
The Big Bang happened 13.8 billion years ago, and then the Hubble sees back to roughly 13.5 billion years. But they see it with galaxies. How do you go from nothing to galaxies? Something must have happened. But we can't see into that, period. It's designed to peer into a part of the universe we have never seen before. The so-called Dark Ages, when everything must have happened. When the first galaxies came into existence, the first stars came into life, the first black holes appeared.
Over time, as the space-time continuum stretched with the expansion of the universe, the light itself is stretched. As that light has crossed the universe, it's gotten redder. And it's been on its way for 13.5 billion years.
Which is why it had to be infrared, because it had to push beyond what the Hubble Space Telescope could see.
Traditional telescopes have mirrors and lenses and things, and they're encased in tubes. The tubes radiate warmth. Any structure you have is by nature warm, just because sunlight falling on it warms it up.
We're back to this. Okay, any questions or comments on that?
So, the universe is 13.8
Billion.
billion light years in diameter.
No, billion years. We're not talking about the diameter. We're talking about the length of time. Just time. 13.8 billion years.
Since it started.
Yeah.
So the younger galaxies are 13.8.
They're less than that.
Huh?
They're less than that. 13. The youngest and oldest. The first galaxies formed would be like 13.4 billion years ago.
It took time for them to form out of the...
Yeah, I have a timeline for that in a minute. We'll go through the timeline of the Big Bang. All right?
My question is, where are we in the universe? Are we in the center, or are we?
Oh, well, those are good questions, and those answers will come in a few minutes.
Okay.
Yes.
Okay, last week you showed us the spectrum of light, whereas, whatever his name, Hubble did that in, Webb expanded it further
Yes.
into visual light. Are there plans for more telescopes and stuff like that to go into the infrared? Have you heard that? If it's
Okay,
in the pipeline or anything?
let me show you this and then I'll answer your question. The answer is, are there more telescopes coming? Yes, because it takes a long time to develop a telescope, right? A couple of decades. So the plans for the next one, beyond James Webb's Space Telescope, are already in place. Now, as to what its characteristics are, I don't know, because I didn't look that up.
But
But let me show you, to get to some of the questions and to move on. This is a slide from the video you just saw. And here it shows, this serves as a timeline of the universe. And we're going to call this a creation story. This is our scientific creation story. It starts with an initial event called the Big Bang. And then some time goes by and the first stars form. There are no stars here, right? There's basically energy here. So the first stars are forming here, and then once you have stars, you can have galaxies, the first galaxies, and then you have what they call modern galaxies. That's anything after the first galaxies, because the first galaxies are going to be different in their makeup than these later galaxies. So I am going to expand on this diagram and give a little more detail in a few minutes. But first, I want to consider another creation story. That's this one. This is the first 5 verses of Genesis 1. And this, I'm not going to read it. You can look at this for a moment. You're familiar with this, I believe. And you know the rest of this creation story too. It has to the creation of plants and animals and then people. But I just put this one up because this is the part that deals with the initial creation. So, have this in mind, and now ask the question, how do the scientific creation story of the Big Bang and this story from Genesis, what's similar and what's different? Any thoughts? Do you notice anything similar? Do you notice anything that's different?
Formless void, but a wind and water.
Okay, that's not mentioned in the Big Bang story.
Light.
Dark.
Light is common in both. Yeah, that's interesting. In both creation stories, light plays a big role. Anything else?
What range of frequencies is light?
Oh, it's in the middle range of the electromagnetic spectrum, and I can't remember what that was. But we can look that up.
So if we're looking at different telescopes, do we look at telescopes that receive different wavelengths?
Oh yeah, the James Webb is getting most of their signals in the infrared, not in the visible. Yeah. And there are telescopes that look in the entire range from the electromagnetic spectrum. All right. Any differences between these two stories? Do you have another similarity?
I was going to say, in the Genesis story, there was nothing,
Yeah.
and then there was something.
Yeah.
And that coincides with...
And now you can debate whether in the Big Bang Theory was the same thing true.
Yeah.
We think, but we
We
don't
had to
know.
start from something.
Yeah. There's an interesting question. Well, here's the similarity. Well, maybe it's not. One interesting question is, what happened before the Big Bang? There's lots of possibilities, but the best answer right now is we don't know. One of the reasons we don't know is with our instruments, with our telescopes, and with our understanding of physics, we can't get past the Big Bang. The physics of the Big Bang is was unknown, basically. Even the physics is, the way things were then. And we have no way of observing back. So right now we can't find out. Yeah.
I think the Big Bang, the thing that was before the Big Bang was the collapsing of whatever existed before the Big Bang.
All right, you just named one of the possible scenarios. Yeah.
So that would be kind of a continuous.
Yeah, that's one. Okay, but there are others. I'm going to want to move forward here because there's one point I want to make. If you haven't seen it. Okay. Then God said, "Let there be light," and then there was light. What's the next thing it says?
So the light was good.
Separated the light from the darkness.
No, God saw that the light
Was
good. Here's a moral judgment. A moral judgment that you don't find in the scientific creation story. Right? So to me, that's a big difference. Now, another question would be, can it be, okay, can both of these creation stories be true in some sense?
Yeah.
Yeah, the truth of these stories depends on the context and the purpose of the story. And so if those contexts and purposes are different, they can both be true in their own. Now, let's have one more creation story. I'm going to have to read this one because not everybody can see it. This is a Chippewa, Ojibwe creation story. When the earth was young, it had a family. Okay, I have to read it here. The moon, or grandmother, and the sun, called grandfather. The earth was a woman, Mother Earth, because from her came all living things. Mother Earth was given 4 directions: east, south, west, and north, each with physical and spiritual powers. When Mother Earth was young, Creator, or Gitchimanadu, as Ojibwe people call him, filled her with beauty. He sent singers in the form of birds and swimmers in the water. He placed plants, trees, insects, crawlers, and 4-legged animals on the land. Gitchimanadu then blew into 4 parts of Mother Earth using the sacred megas shell. From the union of these 4 and his breath, 2-leggeds, or man, was born. Thus man was the last form of life to be put on earth. From this original man came the Anishinaabe, or original people. So there's the creation stories. Is it similar or different from the other ones?
Similar.
It's very similar, isn't it? Yeah. Especially in the order of things happening. And this one had some value too. What was it? There was a value judgment here too. Beauty. The beauty. It was beautiful. Yeah. There was another, yeah.
Didn't they fabricate these stories from things they see around them?
Yeah, yes.
And since they couldn't, there must be something beyond what they see.
Okay, that's a good point. So what was people in both of the Genesis story and the Chippewa story, they did look around to see what it was, right? And they could see the sun and the moon and the earth. They could see them, and so in this story, they gave them special powers, right? Now, what's happening in our modern world? We're expanding, that's a pun, I guess, we're expanding the way we can see. We can see more than people could before because we have figured out new ways of seeing. New instruments, for example. We have microscopes that can look into the very small, but we have telescopes that can look into the very big. And we have learned, as you pointed out, that we're not just going to use visual sight, we're going to use the whole electromagnetic spectrum and get information from other parts of the spectrum. So what we can see has expanded, and therefore our view of the universe has also expanded. And oh, by the way, the universe is expanding besides. So that's where we are. All right, let's move forward and talk about the expanding universe. Now, this is something that came up. Our question comes up, what is the universe expanding into? And the answer is nothing. It's expanding. I went to Wikipedia because I wanted the ultimate authority. All right?
Sure.
The expansion of the universe is the increase in distance between gravitationally unbound parts of the observable universe with time. It is an intrinsic expansion. The universe does not expand into anything and does not require space to exist outside it. Now hold on one second. There's a word here, the observable universe. Remember, because light has got a finite speed, there may be places beyond where a signal can reach us. So we can see a certain portion of the universe, but there may be more than that. We just can't see it, and they can't see us, right? So what stays in this universe, what happens stays in this universe, right? Anyway, so here we have, that's one thing. Now, this idea, if you haven't got your head around this yet, we can have a little cartoon that will show it. Here you have, imagine that these are spheres, and there's a bug on the surface of the sphere, but it's a two-dimensional bug. It only has two dimensions. The surface of a sphere is two-dimensional, right? On Earth we have longitude and latitude. So this bug only knows two dimensions. Now, somehow, it starts out, it's a small universe here, small sphere, and look at points A, B, and C. Now, imagine that we blow up this balloon, and what happens to A, B, and C? They move away from each other. But note that if you're on point A, you see all the other points moving away from you. All the other points are moving away from you. But if you're on point B, what do you see? Same thing. If you're at point B and it expands, you see all the other points expanding away from you. Similarly, if you are on point C and you looked out, you would see the universe expanding, but all the other points of the universe would be expanding. So there is no preferred point. There is no center to the observable universe. It all is the same, right? So that's an important point about the expanding universe. Yeah, Jim?
Just a question. I may have missed something you said earlier. Are those spheres or are they discs?
I want you to imagine it's a balloon. It's a sphere.
Oh, okay, it's a sphere.
And it's a and this is a world, it's an imaginary world of only two dimensions. The creatures on that world, the bug here, are two-dimensional. They're on the surface of the sphere. They can't go up and they can't go down. All they see is their universe expanding. That's all they see. They don't see it expanding into anything. It's just expanding. Now, we can have that's an analogy to what our situation may be, but it's a little bit difficult for us in our world to understand that.
We're trying to use things we understand to describe things we don't understand.
Well, that's what poetry is.
That's where the wrapping of mind. That's where the mind comes.
I won't. There are many things in physics that we don't understand. Yeah.
In this picture, when you have 2 points and they're pretty close together and the balloon is expanding, 2 points that are close together will move slowly apart. 2 points that are a little farther apart are going to move faster. So this is what Hubble learned, was that things that are farther away are moving away from us faster than things that are closer. So you see, like Chuck was talking about the redshift last week, and the redshift is more pronounced for things that we're seeing that are farther away from us.
That in an expansion, like in an expanding universe, we're sitting here on Earth in the solar system. We see galaxies, let's say, that are relatively close to us, they're expanding at a certain rate. But if we see the galaxies that are far from us, they're expanding at a much faster rate. That's what you just said. So that's another key point. And because that's true, Hubble came to an understanding of the relationship between how far something away it is and how fast it's moving. It's the Hubble law. If you know the velocity and the distance, there's a relationship. So if you know the distance, you can figure out the velocity and vice versa. Now we're going to come to that in a few minutes.
Can we assume then that if humans are around millions and millions of years from now, that when we look in the sky, we won't see any stars, or maybe just a few, because everything is expanding away?
I'm smiling because you just jumped to the end of the story.
Oh.
Actually, we're not going to get to that story. But there are some scenarios for what's going to happen far in the future. And they're speculations now because we don't have enough data or theory. But one of them is, we're just going to keep expanding, and it's going to get bigger and bigger and bigger, and light can only travel so fast. So if people could live for, it'd have to be billions of years, they might see the universe expand and it just fades away. And then it looks like we're all alone. But that's one of about a half a dozen speculations about what's going to happen. We're not there yet. Now, this is a more complete view of the Big Bang model. We already covered it. At some point, 13.8 billion years, there's an event that's not completely understood, or not understood at all, but something happened. There was a rapid expansion that I'm not going to discuss. It was a very rapid expansion. But it ended up, this yellow part here is supposed to represent some kind of a mix of energy and light, basically those two things, that's so hot and unbelievably hot. But in time, over time it cools, and as it cools, things can form. You can have elementary particles form. You can eventually have protons and electrons and neutrons floating around in this mix. But at that point, it's too hot. It's too hot for atoms to form. And because this swirling bunch of stuff, there are light, consider light as particles now, these little photons of light bouncing around, but they can't go anyplace. They keep bumping into electrons and neutrons and protons. But now something really interesting happens. It's at this line here, right here, that line where the yellow stops and the dark parts start. What happens at that point, and it was about 375,000 years after the Big Bang. It's amazing that scientists know these things, but they do. At that point, the temperature of the universe was low enough so that nuclei could form, protons and neutrons could get together, and then electrons could be captured, forming an atom. We know what atoms are. Once you have atoms formed, now out of this confusing mass, a lot of stuff is bound up into atoms. Now there's a lot more space for light to get out, and it does. At this point, at this point here, light is able to stream away out into the universe. Okay? Now in a minute we'll see that there's this period here where the first stars would be formed. But that's why they call this the Dark Ages, because there's no stars and therefore no galaxies. Well, as time goes by, these first stars are formed, and the first galaxies are formed, and then we get into a universe as we know it. And remember in that first diagram we had, Hubble could not see back into this area. Hubble was not able to observe things in this Dark Ages period. The Webb telescope is beginning to see that far, and it can start observing the first stars being formed, the first light of the universe. So that's one of the things that they want to do. Now, I want to, we need to, I asked the question, is there any evidence that this really happened? And the answer is yes. No, I forgot what my next slide was. Okay, that's this. Here's what happened. At that point, when light could finally get out and be distributed into the universe, it went out in all directions. And it kept going. So somebody asked the question, can we see it today? And the theorists came up with the idea that yes, we ought to be able to see that signal. But it's taken 13.8 billion years to get here. Yeah, it was a little bit less than 13.8. It's taken that long to get here. And while that's happening, the universe is expanding. And the wavelength of that light that's coming at us from the Big Bang, or just after the Big Bang, that light, though that wavelength is getting longer and longer. It's getting past the infrared, it's getting into the microwave region of the electromagnetic spectrum. So they said, let's look for, maybe we can find that. But they weren't sure they could. Now it's 1965. That was about the time that these ideas, well, maybe they were there before, but in 1965, there were two researchers at Bell Labs out in New Jersey that had a microwave telescope, call it, that was being used for communication, let's say with satellites or something. And they wanted to adapt it to use for astronomy. But they had a problem. There was static in their device. Wherever they looked, there was this buzz. Remember the old days of television when there's static on your TV? Well, they wanted to get rid of the static. That's going to get in the way of what they're looking for. But they couldn't. Wherever they pointed it, they could not get rid of the static. Word got out in the community, and somebody said, wait a minute, maybe that's a signal from the beginning of the universe. And it turned out that's true. It's called the cosmic microwave background. It was predicted to be around 3 degrees Kelvin, and that's exactly what they found.
Wow.
It's exactly what they found. So here, these are images. What happened was that satellites, well, space-based telescopes were made to go out and measure this microwave background everywhere. And this first one, WMAP, I forgot the acronym, this was in 2001, this is later, 2001, more detailed. These are projections, a way of projecting the whole universe onto a two-dimensional plot. What you see here are different colors. This image is kind of manipulated because the actual variation in the microwave background is very tiny, very, very tiny. So they've had to do some processing to get a picture like this. And I'm sure the actual data that they're using is much more detailed. But the point is, this is like a map of the entire universe at the time, 375,000 years after the Big Bang. This is what the universe was like then. And it turns out that those little fluctuations in that background radiation, that they were the seeds for future galaxies. And the structure we see in the universe today basically came from these fluctuations in the cosmic microwave background radiation. I'm almost out of breath here. This is an amazing discovery, and again, this was in 1965. So that's proof. Now, we don't know exactly what happened at the time of the Big Bang, but that event, 375,000 years later, is well observed, is well understood, and has been observed. That leaves great credence to the Big Bang model. And there are other ways of checking that the Big Bang model is correct. I won't go into them. Did you have another?
Just wondering, is that a homogeneous Is this background homogeneous?
Yes, okay, mostly. It's mostly uniform throughout, except for these tiny, tiny, tiny variations. But it's those tiny, tiny variations that are important.
The picture that I'm getting about what's happening here is the galaxies are forming due to the condensation of the expansion of the Big Bang.
No, okay.
I mean, okay.
I think that's right.
Galaxies.
The Big Bang was infinitely hot. And something created, well, here I get my human ability to explain this. Something was infinitely hot and it burst in all directions.
There was an
And then
expansion.
as it burst, things cooled off. And it started, condensation
expansion
started.
of the universe as it got bigger, whatever was there became less dense. And as it became less dense, it cooled, yeah.
Yeah.
And then, at some point, you could have stars formed. We're going to talk about star formation briefly before the time is done here. And once you have stars, then the stars can get together, clump together. The key element here is gravity. Gravity is doing all this work. Yeah.
So where are the microwaves, those little...
The microwave radiation, this is radiation that came from just after the Big Bang. It's
okay, in the cooling?
It's right here in this room.
What's sustaining it?
Huh?
What is sustaining that background?
Yeah.
It came out of the Big Bang.
Yeah,
And
that's where I
it's just
wanted
there.
you to start.
Yeah.
it's just there.
Yeah.
Yeah, I just wanted you to
Because we could
go
do
back.
It's floating through back in '65, they had this microwave telescope, and wherever they looked, they got this sky. It's hitting them from all directions. I'm going to keep moving on. Yeah.
What about black energy and the big rip theory?
Okay.
I'm only 2 slides away from you. We're not going to talk about the Big Rip, but we will talk about dark matter and dark energy. You didn't hear that yet. He knows what's coming. You guys haven't heard it yet. Okay. All right.
Not gonna give a rip.
Okay. Actually, we're only 1 slide away. So we want to know, how fast is the universe expanding? If it's expanding, let's measure it. Now, Hubble knew that Hubble had known since 100 years ago that if you could actually measure the distance to find out how far away it is, you can also measure the velocity using this redshift business in the spectrum. So if we could really know how far something was and then measure its velocity, then remember, when we look out, we can find galaxies at various ages, right? The really, really old ones, the entire time spectrum, we can find galaxies. So what we need is we need a way to find the distance to the most distant galaxies. Independent of their velocity, because we want to also know their velocity. How do you do it? Now there's this concept called a standard candle. They're not using candles in astrophysics, it's a term. But it's easy to explain.
It's a unit.
If I have a 100-watt light bulb, I know how bright it is. It's called its luminosity. If I give Canute a 100-watt light bulb and tell him to walk way far away, what's going to happen to the light from that light bulb? In my view, it's going to get dimmer. It'll get dimmer. Now, if he's out there and I can measure the luminosity of that light bulb, I know what the real luminosity is. That's the apparent luminosity. And that light will be reduced by a certain amount. If you're a physics teacher here, you can tell me how much it's going to be reduced.
We don't teach that.
You don't teach
You
that?
skip over that.
You skip over that.
Too many questions, eh?
How much is it going to be? How much is the light going to be reduced? It's involved the distance.
It's an inverse square.
It's an inverse square law.
Oh, yeah.
So it's if it's d away, then you don't divide the luminosity by d. You divide it by d squared. this, okay? We know how the light is going to be reduced. So I know that. So if I know what that luminosity of that light bulb is, I can figure the distance. So we want the equivalent of that light bulb out in some galaxy way a long time away, far away. But wait a minute, galaxies vary in size and in luminosity. But it turns out there are two things that don't. One is called a Cepheid variable star. These were discovered early. That was, what's her name, Henrietta Leavitt. This woman 100 years ago or more discovered that there's a kind of star that varied. It varied in brightness. And moreover, she discovered a law that associated the brightness with the period of how it varies. So if you could now look at find a Cepheid variable star, see how fast it's varying, and based on that, you know how bright it is. So you know the brightness of a Cepheid variable star. And if you can find one in a galaxy, now you can find the distance very accurately. Except that they're hard to see when you get way out there. So there is another kind of object that has consistent brightness, and that's called it's a particular kind of supernova. A supernova is when a certain kind of star explodes. And when that happens, it gets really bright. And there are some of them that, for various physical reasons, always have basically the same brightness. So using these techniques, in about late 1990s, almost to the turn of the century, 1990s, almost to 2000, there were two teams of astrophysicists that were using these techniques, looking at supernovae in most distant galaxies, to figure out how fast the universe was expanding. One of the things they were looking for, or asking the question, is the expansion slowing down? Because there's still gravity, it goes out, maybe it's going to reach a point and then start shrinking again, right? Just like if you throw a ball up in the air, it'll go up, but as it goes up, it'll go slower and slower and slower, then it'll come down. So that's one scenario, that the universe will start shrinking, and it'll come back, and that's called the big crunch. The big crunch. And then presumably, then it might bounce and go back again. So they want to know, well, let's see, is it going to just keep going the way it is, or is it going to slow down? So this is about 1998, I think. They discovered the expansion of the universe is accelerating. It's not slowing down, it's getting faster and faster. So here's a little cartoon diagram, right? For a long time, the expansion was decelerating, then it maybe started to accelerate, and now we realize that it's actually accelerating. So, nobody ordered that, they didn't expect that, because there's got to be something that causes this acceleration. It takes energy to accelerate a universe, right? So what was it? Well, they had already talked about dark matter, and we'll have a few words to say about that. I mentioned it last week. Dark matter is, there's matter out there, we don't know what it is. It doesn't shine, it doesn't reflect, it doesn't reveal itself except through gravity. So the people here said, we're going to call this dark energy. Oh, we have dark matter, let's have dark energy. They're not the same. So dark energy is what's causing this expansion. So here's a better picture of the Big Bang model, because it does show, now, it shows this accelerated expansion here. And that's due to, well, it's caused by something called dark energy. Now, they're not sure what it is. There's some ideas, and they're being tested. But here's all of them. Yeah, I'll let it go at that. I think I have a slide on dark matter, yeah. This stuff called dark matter, we know it exists from two things. When the astronomers look at a galaxy, they can see the stars in the galaxy. They're shining. The light is coming out. So they look at a galaxy, and they can estimate how much mass is in that galaxy based on what they see. Then they do theoretical models. Here they're probably doing computer simulations to see if you have this much mass, and there's other characteristics, well, can you get the shape of the galaxy you're looking at? And what they found out was, no, if that's all the mass you have that you could see, there's no way that galaxy can form the way it is. There's got to be more mass there that we can see. And that was one example of dark matter. The other way, and I showed you this last time, is through something called gravitational lensing. I did that with waving my hands. Here's a picture. I don't know if you can see it, but over here, these are three examples where the far left you have a distant object, a star or something. And on the far right you have Earth with a telescope. And in between, remember this is a long ways away. In between there are three scenarios here. Let's look at this one. In between you have a glob of mass, something very large, but you can't see it. But it's there because you can see its effect. What happens when light goes by a huge mass, it's going to bend. It's going to bend. And so that becomes a lens. And that lens will cause certain patterns in what you observe. And here's an example. It's got these streaks. Remember I said some of those are lensed objects, and some of these streaks might actually be of the same distant object because of this lens. Well, if you didn't follow that, don't worry about it. The point was, there's something called dark matter out there that we don't know about. And now here's the interesting thing. People say, all right, well, we've got normal matter that we can see, and we're made out of the normal matter. Then we've got this dark matter that we don't know about, and we also have dark energy. Now, you remember from Einstein's work, E equals mc squared. Basically, matter and energy are the same thing. They're just kind of different forms. So you want to add up how much stuff is there in the universe. And here, and they did, they added it up, and here's what they came up with. Ordinary matter, like you and me and the moon, that's about 5%. About 27% is dark matter that we don't know about. I think it's here in the room, so if you see any, let us know and you'll be famous. And then there's dark energy, that's 68%. So, we don't have all the answers today in this forum. These are things that are not known, they're mysteries, but you know, scientists love these things because that means there's some interesting things to do.
Yeah.
So we have to find out, scientists have to find, we do, to find out what is dark matter, what is dark energy. There are ideas, there are things to work on, there are things to check, experiments to do, theory to do. So that's all happening. Yeah.
I was just wondering, could this dark matter, I mean, there's such a thing as subatomic particles like quarks and muons and whatever.
That's one of the ideas. It's some elementary particle that we don't know about yet. And so they might want to use these atom smashers, these colliders, like the one in Switzerland, to look for that. But right now, those don't have enough energy to get into the realm that particle would be seen. But that's one.
That's the God particle?
Actually, it has a name. They call those WIMPs. wiggly, interacting, massive particles. It's a WIMP.
Okay.
You want to know what another one is? And I'll forget the acronym, but it's called a macho. It's sort of like a big particle, like for example, the leftover of a small star. After the star dies, it becomes something called a brown dwarf. It doesn't reflect much, you can't see it. It could be a lot more than we think. These are ideas for dark matter, and they're being worked on and tested, but we don't necessarily have the theory or the experimental ability just yet, but we will sometime. Yeah.
Just to form a comparable thing, we can see we can see light in a certain portion of the electromagnetic spectrum, but we don't have anything that we can see with the dark energy.
Right.
In other words, whatever portion of the electromagnetic spectrum that is,
it's irrelevant to the dark matter.
We have no detector for that.
Yeah, exactly right. That's exactly right. Yeah. All right, I have one more slide that will leave you with things to ponder.
All right.
Oh, what's coming is a lot easier.
That's right. That's right.
Look at this slide.
Yeah.
You may have seen this before. This came from the Hubble telescope. It's called the Pillars of Creation. In the Eagle Nebula, a nebula is an area where there's lots of dust and gas, and it's inside the Milky Way. It's not outside. It's in the Milky Way, but it's a place where stars are going to be formed because there's lots of dust and gas around. And here's how a star is formed. You have all this dust and gas, and it's interacting via gravity. And so something might happen. Maybe for some reason some of this gets together and gravity pulls it together. Once you get things started, that little clump of gas starts getting a little bit more massive. And when that happens, it attracts other dust and gas. Pretty soon you have a ball of gas that's contracting, right? It's contracting. And then at some point, it gets bigger and bigger and bigger, and in the middle of that ball, it gets starting to get real hot and real dense. And at some point, it's so hot and so dense, and a lot of this is hydrogen, let's say, that you start having fusion. Two hydrogen atoms fuse together to form a helium atom. And that fusion reaction releases energy. This is the mechanism that we humans use to make hydrogen bombs. Right? So now you've got this fusion happening, and the energy from the fusion balances the incoming pressure from the gravity. So you have a balance between nuclear energy, nuclear forces creating energy that's pushing out, and the gravity coming in. Now you have a star. Now wait 5 or 10 billion years, and all the fuel that can be fused together is gone. And now the gravity can no longer be resisted, and it squeezes the star down, and in many cases it will cause the star to explode. Right, so the star explodes, and all the atoms in the star and whatever planets are around it are blasted out into space. Now, once that happened, those atoms become part of the dust in space, and later might coalesce into another star. Right? So this is the fun part. Except for hydrogen, all of the atoms in your body were formed in another star that existed before the sun. Hydrogen might have come from the Big Bang, but anything bigger than helium, let's say, came from inside a star. Actually, not even inside a star. The real heavy elements, say something like iron, wasn't formed inside a star. It was formed when a supernova exploded. Okay? But whatever it was, the elements that are available for the sun and the planets were formed in a star before the sun. Now, in about 5 billion years or so, the sun is going to become a nova, it's going to explode. And all the elements that are currently in this earth, and in you and me, are going to be blasted out into the universe and will become part of the dust of the universe. I'm being a little poetic here, but I'm trying to be.
Okay.
So, that's in the future. It's going to be a while. Don't hold your breath. Don't worry about it. But that's what's going to happen. Now here's the question. We don't know exactly all those things, and we don't know when these things are happening, but what we do know is this. In a couple of months, it's going to be Ash Wednesday, and you're going to go to the altar, and you're going to hear the words, "For dust you are, and for dust you are to return." You've heard that before, right? Now that you know, think about what it means when you know where that dust came from. Where did that dust come from? That you are. And where is it going? That's the thought I leave you. Does anybody have an initial reaction to that?
Recycling. Well, the great recycling of God.
What?
The great recycling of God.
There you go.
Yeah. All right. Yes.
So the condensation of this image we're seeing here, is that kind of analogous to a raindrop forming? A raindrop forming? I mean, doesn't a raindrop need a little particle of dust?
Oh, yeah, I think,
to condense?
yes. That sounds like a good analogy, yes. Yeah.
Chuck, when you were talking about dust to dust and, going back, is that what people use for reincarnation stories?
That's...
I thought of that when you...
That could be, yes. Somebody could and probably has used that in a reincarnation story.
That's what I thought of when you started talking about it.
But also, there's ideas of cyclical universes, right?
Yeah.
Okay, so there's several, we mentioned, for the far future, we mentioned a couple of them. But there's other things going on in the future. And in 2 forums, we've just scratched the surface, in a sense, of what we could be talking about. I mentioned, looking for life on other planets. Well, that's an interesting story, and it has interesting repercussions. So,
when we become,
one last question.
What?
They want our dishes, huh?
When we become dust, then we'll know.
I did this class before, a broader class, and one of the last Bible passages that I had for people to think about was, Craig will help me out here, 1 Corinthians 13, that's the love chapter. Remember, the love chapter? And at the end of that it says, "For now we see in a mirror dimly, and then we'll know face to face." So if we could wait 5 billion years,
indeed,
let's gather again and we'll see how well these theories have worked out.
It's Pastor John's answer.
Yeah.
When you get to heaven, you can ask him when you get there.
Yeah.
Then we'll know.
Yeah. Thank you.
Thank you, Chuck.